The latest image of the interstellar object 3I/Atlas, captured on November 5, 2025 by the Lowell Discovery Telescope in Arizona, has added a new level of complexity to the already puzzling scientific narrative surrounding this object. At the time of observation, 3I/Atlas was located 1.38 astronomical units from the Sun and 2.23 astronomical units from Earth, distances that still allow high-precision measurements, but usually challenge ground-based telescopes to extract meaningful structural details. Nevertheless, the Lowell Discovery Telescope obtained an image in which the object appears as an intense point of light, roughly the size of the telescope's point spread function, suggesting that the core of the object is extremely compact or that any surrounding structure is too faint to dominate the image. Around this bright nucleus is a subtle, diffuse halo, something reminiscent of a thin atmosphere or a modest cometary coma. Yet this halo is faint enough that its exact nature remains ambiguous. The green filter used during the observation, which is specifically optimized to detect the presence of C2 molecules, did show activity in the form of a glow, and the brightness was even stronger in the bluer filter, indicating scattering by tiny particles or gaseous emissions. Despite this, there was no clear evidence of a comet-like tail, no elongated dust structure pointing away from the Sun, and no streaming plume that would ordinarily be expected from a highly active comet experiencing strong solar heating near perihelion. The absence of such a tail is striking because natural comets undergoing substantial sublimation should exhibit obvious, directional behavior produced by radiation pressure and solar wind. In fact, given that NASA's Jet Propulsion Laboratory has formally reported non-gravitational acceleration acting on 3I/Atlas, one would predict that substantial mass is being expelled from its surface. According to momentum conservation, a comet showing measurable deviations from a purely gravitational trajectory must be shedding material vigorously, and calculations suggest that more than 13% of the object's mass would need to have evaporated during perihelion if the acceleration is driven solely by outgassing. The release of such a massive amount of mass, especially under the extreme solar heating of nearly 770 watts per square meter, should have created a visibly prominent coma and tail, easily detectable even from the ground. Instead, the current image shows only a round, nearly symmetric glow, with no directional features. This observational contradiction forms the core of the mystery. How can an object supposedly losing more than a tenth of its mass exhibit almost no visible sign of cometary shedding? One potential partial explanation involves the geometry of observation. When the November 5th image was taken, 3I/Atlas was only 13 degrees away from the Sun in the sky, meaning observers were looking at it nearly head-on along the same direction that a tail would extend. A comet's tail always points away from the Sun, and when the Earth lines up almost perfectly with that direction, the tail appears foreshortened, compressed into a bright but subtle haze, rather than a long, sweeping line. Under such conditions, even a strong dust tail can become visually diminished, leaving only a compact halo similar to the faint glow seen in the image. However, while this geometrical argument might seem convincing at first glance, it becomes less satisfying when compared to earlier imagery of the same object. On July 21, 2025, when 3I/Atlas was at an even smaller angular separation of just 10 degrees from the Sun, the Hubble Space Telescope was able to detect a distinct anti-tail extending sunward, elongated by a factor of 2 relative to the object's core. This anti-tail is a well-known phenomenon caused by large dust particles that follow slightly different orbits and can appear to stretch toward the Sun due to the viewing angle. Given that Hubble saw such a clear sunward structure under almost identical angular conditions, the absence of any similar elongation in the Lowell image raises serious questions. If anything, one would expect the object to display even more dramatic features now, since perihelion heating should have increased its activity, not diminished it. The contradiction between expected behavior and observed behavior forces scientists to consider possibilities beyond simple geometry. The next few weeks are expected to provide crucial clarity. As Earth's position relative to the Sun shifts, The angle separating 3I/Atlas from the Sun will increase to several tens of degrees, giving observers a more side-on perspective. With the viewing geometry improved, any existing tail should become unmistakably visible, enabling a confident assessment of whether the object is shedding dust and gas like a natural comet. If a tail appears, it may confirm that the object is behaving normally and that the earlier lack of visibility was merely a line-of-sight effect. But if no tail emerges, even when the sun-object angle is large, the implications will be profound and potentially disruptive to conventional comet physics. Such an outcome might indicate that the object contains surprisingly few volatile materials, or perhaps that its surface is sealed under an unusually tough, refractory crust that suppresses outgassing. Alternatively, it may suggest that the non-gravitational acceleration observed is not caused by sublimation at all, but instead by some other mechanism, such as a highly reflective surface experiencing radiation pressure differently than expected, or an exotic physical process not typically associated with natural comets. The behavior of interstellar objects has been a topic of intense scientific interest ever since the passage of 1I/Oumuamua in 2017, which also displayed non-gravitational acceleration without showing a visible coma or tail. The similarities between Oumuamua and 3I/Atlas, two interstellar visitors whose behavior does not fully align with established cometary physics, inevitably raise comparisons. Both objects challenge assumptions about how extraterrestrial bodies should behave when heated by the sun, and both exhibit characteristics that lie somewhere between comets and asteroids, defying easy classification. In the case of 3I/Atlas, the reported mass loss estimates, combined with the absence of a tail, highlight a tension between theory and observation. If more than 13% of the object's mass truly evaporated, there should be overwhelming evidence of dust and gas around the object, yet the telescope shows only a compact glow. Even accounting for observational angle, the discrepancy is difficult to ignore. The faint halo detected in the green C2 filter does indicate some level of gaseous activity. C2 is a common emission product in cometary atmospheres, formed when sunlight breaks down carbon-bearing molecules released from the surface of the object. However, the brightness of such emissions is usually proportional to the level of outgassing, and the subtlety of the halo hints that the activity may be far lower than expected for the inferred mass loss. This inconsistency deepens the mystery. How can the object accelerate as if it is losing huge amounts of mass, while simultaneously showing only minimal signs of actual mass shedding? Perhaps the object's material is distributed differently than assumed, or maybe it releases gases episodically in bursts rather than continuously. Or, more provocatively, maybe the source of acceleration is not mass loss at all. These open questions have fueled widespread public interest. According to the statement, hundreds of letters were received on the day the image was released, reflecting a global fascination not only with interstellar objects, but with the possibility that our understanding of them remains incomplete or flawed. Enthusiasts, researchers, and amateur astronomers alike are waiting eagerly to see whether 3I/Atlas will eventually reveal a tail, or whether its behavior will remain enigmatic. Over the coming weeks, more observations will be made, and with a larger angular separation from the sun, the true nature of the object should become more apparent. If a tail finally appears, it will validate the cometary model and settle much of the debate. But if no tail emerges despite ideal conditions, scientists will need to seriously reconsider the fundamental processes driving non-gravitational acceleration and perhaps revise long-standing assumptions about interstellar bodies. For now, the mystery of 3I/Atlas remains unresolved, hanging in a delicate balance between conventional explanation and the possibility that something unusual, and perhaps unprecedented, is taking place as this enigmatic interstellar object moves silently away from the sun, leaving behind more questions than answers.